A very warm welcome to MA2001 Mechanics of Materials tutorial. I'm your tutor, Professor Ng Bing Feng. In Mechanics of Materials, we will study the stresses in structures as they are subject to external loading and how they behave or deform as a result of these stresses. As we go through the tutorials, you'll realize that concepts are built up from the fundamentals of axial loading, torsion, shear, and bending in the first 4 chapters, which are then applied to structures together to solve more complicated problems in subsequent chapters. Mechanics of materials is not mathematically demanding, and a lot of the steps are standard, which can be applied across all the problems you will encounter in this course. However, the problem that most students will face is in the visualization of how external forces will lead to different internal stresses. This is something which you will need to train yourself for. In tutorial 1, we'll cover the concept of stresses. In this course, we are only considering static equilibrium. Static refers to zero velocity, meaning stationary. Equilibrium refers to a case where all the forces and moments are balanced in all directions and axes of rotation. Mathematically, we write this as the summation of forces in any direction to be 0 and the summation of moments about any point to be 0. Forces are straightforward and is mass times acceleration. For moments itself, it is the product of the magnitude of the force to the perpendicular distance from the force line of action to the axis of rotation. For example here, for moments, if force is 10 newtons and is at a distance 2 meters away from the axis, the moment itself is just 10 times 2. There is a difference between moments and torque. Let's take a look at an example here. The object of interest is a column. The axis that runs through the center of the object in the direction where the object is longest in length is what we call the longitudinal axis. The axis that runs along other directions is the lateral axis. If we have a force that's applied on the gray color arm over here, it will create a rotation about the longitudinal axis, and this is what we call torque. If instead the force is applied in this direction instead, it will create a rotation about the lateral axis, and this is what we call moments. In this course, we will need to draw a lot of free body diagram. A free body diagram is an illustration of how different forces act on the object of interest. The forces to consider are the body weight, external loads, and all forces across the boundary of the free body diagram. Internal forces are not considered. We'll take a look at this further. This is an example from your notes. You are given a triangular frame with a force of 30 kN at the tip. To draw the free body diagram, we first draw the structure of the beams over here. There's no need to draw the walls, or if there's floor, there's no need to draw the floor. Next, we draw the forces acting on the structure. First, we'll include the body weight, and here, since we're assuming the structure is weightless, there's no need to draw the weight. If there's a weight, we'll need to include. Next, we'll include the external loads, and in this case, it is the 30 kN over at the tip. Then, we'll need to include the forces across the boundary, which are the reaction forces. As the reaction forces act on the wall and also on the beam itself, there will be equal and opposite forces over here at the boundary. And this supports itself as we are not sure of the direction and magnitude. Therefore, we assume that it acts in the positive x as well as the positive y directions for C and for A. There will be internal forces over here at the junction B. But since we have considered the structure as a whole, these internal forces will not be considered. Unless we take out beam AB itself, where you can see over here, then the reaction forces at B, which is the internal forces, will need to be considered. There are in general two kinds of objects we consider in this course. First is the tie or strut, which we call two force members. When we say two force members, it means that there are only two forces acting on the object. However, just having two forces, the question would be, would it be sufficient to keep the object in both force and moment equilibrium? It turns out it is possible. And this is when the two forces are pointing away or towards each other along the longitudinal axis. This leads to compression and tension. To achieve or identify objects that are two force members, they must satisfy some conditions. The first condition is that it must be pin-ended, meaning the ends are attached by pins or pivots. There should only be axial or longitudinal forces pointing away or towards each other. There must be no transverse loading between the pins and hence no bending or moments. Also, we need to assume that it is weightless, which otherwise there is the third force of weight. The reason why we consider two force member is to help simplify a problem. Typically, at a joint, we do not know the direction of the resultant force. But if we are able to identify if an object is a two force member, we will then know the direction of the force. That makes things simpler to solve. For all other objects that have multiple forces, pin, fixed end, has bending, has weight, we will call them beams. As you have seen earlier, for two force members, the two forces must point away or towards each other to keep it in equilibrium. If the two forces do not point towards each other, there will be rotation in this case. It calls for additional forces or moments to keep it in equilibrium. Hence, this is not a two force member. Same for this, where the forces at the ends are pointing upwards, it has to be balanced by a force that points downwards to keep it in force equilibrium. This is also not a two force member. Let us go back to solve the problem you saw earlier. This is also the question in your lecture notes. In all the problems you see in this course, it will be in equilibrium. As such, the sum of forces in all directions and the sum of moments about all axes is 0. For this problem, let's first take the summation of forces in the x direction to be 0. We have ax plus cx equals to 0. We then take the summation of forces in the y direction, which we have cy plus ay minus 30 equals to 0. There are 4 unknowns and only 2 equations. As such, we cannot solve. So now we move on to the summation of moments. The intention is to find an equation that we can solve directly or is able to solve simultaneously for the unknowns. For the summations of moments about A, we only have one unknown, which is Cx. For the summation of moments about C, we also have one unknown, which is Ax. As such, we are able to solve for Cx or Ax. In the exams of CA, the problems given to you will definitely have a solution. If taking of forces does not work, you should try to take moments about different points until it works. Let us take summation of moments about the point C. For summation of moments about the point C, it is equals to Ax times 0.6 in the anti-clockwise direction minus away 30 times 0.8 in the clockwise direction. Solving, we get Ax equals to 40 kilonewtons. As this is positive, we know that the direction we assumed previously is correct. We then take the summation of forces in the x direction, Ax plus Cx equals to 0, and find out what Cx is. Cx turns out to be negative 40, which means that the direction we assumed previously should be reversed. Cx should be pointing in the other direction instead. Now that we have AX and CX, we still cannot get AY and CY because there's only one equation and two unknowns for the sum of forces in the y direction. So, we break down the problem to look at the individual components. This can be AB or BC. Let's take a look at AB. When we do so, we will need to include the internal force at B. Without considering the internal force at B, the beam AB will not be in equilibrium. As such, we will need to consider the internal force, which is Bx and By. Taking summations about B, it will be AY times 0.8 equals to 0, and we obtain AY equals to 0. After which, we take the summation of forces in the y direction to be 0, and we get Cy equals to 30 kilonewtons, which is positive, and it means that Cy itself is in the correct direction. The previous way of solving can in fact be simplified. If you remember, we have explored two force members. Here, AB and BC are pin-ended and there are no transverse forces and are assumed to be weightless. As such, we can assume AB and BC to be two force members. When we do so, it means that the forces act along the longitudinal axis of the rod. From there, we can make use of the method of joints where all the forces meet. The point where all the forces meet is at B. Here, we have a known external force of 30 kilonewtons, which is downwards. For FAB and FBC, we know that they lie along the longitudinal axis of the rod. However, which direction they are pointing along the axis is not known yet. In the methods of joints, we extract these forces acting at point B to form a triangle. In the triangle, only the direction of the external force, 30 kilonewtons, is known, so we put it in. Because the system is in equilibrium, therefore forces must cancel, and hence we draw a circle. The direction of the circle, the direction of rotation of the circle, is determined by the direction of the external force or the known force of 30 kilonewtons. As such, it will rotate in the anti-clockwise direction. This rotation will also determine the direction of the forces along BC as well as AB. After that, we can make use of the sine rule. A over sine theta A equals to B over sine theta B equals to C over sine theta C to solve for the unknown forces, provided that the angles theta A, theta B, and theta C are known. This is the fourth triangle from the previous page. We translate the forces to act at the point B. So now the question is whether FAB itself is in tension or compression, and FBC is in tension or compression. Just by looking at the direction of FAB, you have thought that FAB itself is in tension. However, the forces from methods of joint act at the joint on the pin. The forces in the beam are in the opposite direction due to equal and opposite reaction forces between the rod as well as the pin. As such, the stresses in AB will be in compression. Likewise, for BC, the direction of forces will be opposite to that acting on the pin, and BC will be in tension. As you've seen from the previous example, as forces act along the longitudinal direction of the rod, there will be stresses acting on it. Forces normal to the surface of an object will create normal stresses. If the force is a concentrated force, the normal stress itself will not be evenly distributed along the cross-section. As such, every point along the cross-section will experience a different normal stress. For simplicity in this course, we assume that the normal stress is uniform along the cross-section, which is equal to the average normal stress, which is sigma average equals to force over area. Normally, we will want the force to be not so large such that it exceeds the yield stress of the material, which is a permanent deformation of the material. Or we also want the force not to be too large that it exceeds the ultimate stress, whereby the object will fail. Typically, if the force acts along the centroid of the object, the stress can be assumed to be uniform along the cross-section. This is called centric or concentric loading, where normal forces only cause normal stresses and there's no bending. We look at the yellow arrows here, which is evenly distributed along the cross-section. If, however, the force does not act along the centroid of the section, it will cause eccentric loading. In this example, if you see in the notes, we have the force that acts over here. This itself is at a distance d away from the centroid that we want to consider. Because the force does not act through the centroid that we consider, the forces itself can be broken down into an axial force that acts along the centroid plus a moment. The stresses created will be the sum of the stresses due to uniform loading plus the normal stresses due to bending, and this itself is the resultant stress at section C. Do not worry about the drawings here, which will come in at later chapters. Another concept that's introduced in this chapter is shear. If the two forces act in the direction shown, there will be stresses at section C, where AC will want to slide past CB in opposite directions. This stress is known as shear stress. For shear stress, is defined as tau equals to P over A. P here, the force is tangential to the surface, and the area is where the tangential force is applied and where the shear stress will be observed. There are two kinds of shear. There is the single shear, where there is only a layer that's sliding past each other. Area A is trying to prevent the top and bottom from sliding due to the force P. There's also the double shear, where there's a top and bottom layer to prevent the center layer from sliding. In double shear, the shear stress itself is half that of the single shear, because there are two areas preventing the sliding motion. In this chapter, we also considered bearings, and we'll need to know what are bearing stresses. Bearing stress itself is the average stress that is perpendicular to the cylindrical surface. In other words, it's the force divided by the projected area from the cylindrical surface, which is the area you see over here. If we consider normal stresses instead of bearing stresses, normal stresses is perpendicular to the cylindrical surface. In other words, it will act perpendicular in all directions of this cylindrical surface. This itself will be rather tedious to compute because we need to find out what is the angle as well as the stress in all directions. As such, for bearing stress, we simplify the problem by taking the projected area and subsequently taking force divided by projected area to get our bearing stress. When we have pin-ended objects, critical stresses on the object will depend on whether the object itself is in compression or in tension. For the same magnitude of the force, if it's in tension, maximum stresses are typically higher in tension than in compression. If you can take a look at the equation for stresses, sigma equals to P over A. For the same force itself, sigma will be maximum if area is smallest. In tension itself, the critical area is over here, and in compression, the critical area is here. As such, in tension, the critical area is smaller, and the stress itself will hence be higher. Let us take a look at an example here. If an object itself is in tension, and it's actually pin-ended, the pins itself will touch the object on the outer edges of the hole. As such, the affected region under tension is over here. Maximum stresses will occur where the area is smallest. And within this affected region, the smallest area is over here. If in compression itself, the pins will touch the circle on the inner edges. As such, the affected region under compression is this region. Stresses will be maximum if area is smallest, and in this case itself, the area is the same throughout, and hence the stresses or the compressive stresses will be the same. If you have forces P acting on the beam, and you consider stresses along different planes of the cut, if the plane of interest is perpendicular to the force, as you can see over here, the area itself given by A0, the normal stresses along this cut will be P over A0. Because there is no component of forces parallel to this area A0, there will be no shear stresses. As such, tau will be 0. At this plane perpendicular to the forces, sigma on the normal stress will also be maximum. If instead we consider a plane of cut that is at an inclined angle, say theta, the area of this cross-section will be A0 over cosine theta. The forces on this inclined plane will correspondingly be broken down into a component that is perpendicular to the surface, P cosine theta, and parallel to the surface, which is P sine theta. The stresses normal to the inclined plane will hence be P cosine theta divided by the area A0 over cosine theta, which gives us this equation here. The stresses that is tangent to the inclined plane, which is also the shear stress, will just be P sine theta divided by the area, which is A0 over cosine theta, and you arrive at this expression here. Just nice, at 45 degrees, you'll find that the value of shear stress on the inclined plane itself is maximum among all the values of theta. This value of maximum shear stress at 45 degrees plane is also half that of the maximum normal stress on the perpendicular plane. The corresponding normal stress at the 45 degrees plane is also half that of the maximum normal stress on the perpendicular plane. In this course, you will also be asked to draw elements. You can imagine elements as taking a marker and draw a square on the surface of an object as it undergoes compression or tension. If the object undergoes tension, the element's left and right faces will experience normal stresses, and as such it will stretch in a way that will become a rectangle. If instead you draw a diamond, the sides of the diamond will experience both shear stress and normal stress that will cause it to elongate in such a way that you see over here. Another concept you need to know in this chapter is factor of safety. This number is a multiplier for the allowable stress before the object will fail. If your object fails at say 10 Pascal, this will be your ultimate stress. You will not want to have loaded it to 10 Pascal because it will be at the borderline of failure. Instead, you will want to set a factor of safety to allow you some buffer. Say if you set a factor of safety of 2. As such, it will only allow the object to be loaded by 5 Pascal so that you have some distance away from failure. Let us now look at the tutorial questions. In this question, 1.2, there are two cylindrical rods, AB and BC, which are welded together. We need to determine the average normal stress at the midsection of AB and BC. As you can see, there are two forces acting on the object. One that is 240, 120 plus 120, which is 240 in compression, compressing BC, and another one that is 160, that's causing tension along A, B, C. When you encounter problems that have multiple forces, you always start from the free end. From the free end itself, in the free body diagram number 1 you see over here, this section AB will experience 160 kilonewtons only. For the free body diagram 2, the section BC will experience both 160 kilonewtons tension and 240 kilonewtons compression. Students normally ask, how come I do not consider 240 kilonewtons to add on section AB? The reason is simple. For an object to experience stress, there must be an equal and opposite force on both sides. Here, the 160 kilonewtons has an equal and opposite reaction force from the wall on the right side. Hence, the hole A, B, and C will experience the 160 kilonewtons force. The 240 kilonewtons compressive force will also have equal and opposite reaction forces from the wall. On the other hand, there is no equal and opposite forces on the left side of the free end to balance the 240 kilonewtons. The end A itself is free, and there is no reaction forces here. As such, only BC itself will experience compression from the 240 kilonewton stress. For section AB, the normal stress is thus 160 kilonewtons, that's in tension, divided by the cross-sectional area as given here. This gives us 81.5 megapascal in tension. Normally tension we put as positive and compression we put as negative. But you can also put the words tension in brackets by the side. For section BC, it will experience 160 kilonewtons in tension and 240 kilonewtons in compression. As such, we minus the forces away and we get 80 kilonewtons in compression. The normal stress is thus the force divided by the area, which gives us negative 18.1 megapascal. We can also write it as 18.1 megapascal compression. The next question shows a T-shaped object, as you can see over here, where there's a force P acting on the right side. At A itself, there's an 8 mm pin, and at B and D, there are 12 mm pins. We are asked to find the allowable load P such that the stresses in the pins do not exceed the ultimate shear stress of 100 megapascal. And we also have a factor of safety of 3 we have to consider. We also need to ensure that the force P itself will cause the normal stress in links BD to not exceed the ultimate normal stress of 250 megapascal with a factor of safety of 3. We'll first try to simplify the problem through observations. Here, it is clear that ABC itself is not a two-force member because there are transverse forces at the center. However, BD itself is a two-force member. Hence, this is the free body diagram. At A itself, because we do not know the direction of the force, we assume AX and AY. At D itself, we are only left with DY because we have known that BD is a two-force member. We are told to find P subject to the conditions of stresses in the pins as well as the links. As such, we will need to find the unknown forces AX, AY, and DY. If we take moments about A, we are only left with DY. The expression will be dy times the distance AB is in the anti-clockwise direction, as such we put a negative sign, plus P times the distance AC, which is 380, and this is in the clockwise direction. And we let it be equals to 0. We obtain this expression here. We then take the summation of forces in the y direction. Ay plus dy minus p equals to 0. And after some manipulation and rearranging, we arrive at Ay equals to negative 9/10 p. For summation in the x direction, Ax is only present and hence Ax is equals to 0. We will first solve for the shearing stress condition. At A, there is only the force Ay, which is equals to negative 9/10 p. Since it's negative, it's acting downwards. We have also found that Ax itself is 0. The pin at A from the question, as you can see over here, is a double shear. We are told that the stress in the pin itself must not exceed the ultimate shear stress divided by the factor of safety. The allowable shear stress over here is given by Ay, which is this expression, divided by 2A. There's a 2 here because of the double shear. Upon solving this equation and substituting in the expression for Ay, we obtain P equals to 3.72 times 10 to the power 3 newtons. At B and D, we have the same condition. We also have double shear for the pins. Hence, we only need to solve for one of them, which we choose pin D. Pin D itself will experience the force dy. As such, using the same equation, dy over 2a equals to the ultimate stress divided by the factor of safety. We substitute in the expression we found previously for dy, which is 19p over 10, and subsequently solve it, and we find that p equals to 3.97 times 10 to the power 3 newtons. We now solve for the normal stress conditions in the link BD. The force in this link BD itself is given by dy. dy is also a two-force member. As such, the normal stress expression, allowable normal stress, is equals to the ultimate normal stress divided by the factor of safety. Since there are two links, as such, dy itself will be divided by 2a. The allowable stress will be dy over 2a. We substitute in the expression for dy, which is 19p over 10, and then we solve, we obtain p equals to 14.04 times 10 to the power 3 newtons. We now have three forces, and we normally choose the smallest one because it fulfills all the conditions. If we choose a higher force, then you will violate some of the other conditions. In this question, we have a triangle link. We have 40 kilonewtons acts at the pin. We are also given the diameter of the pin as 20 mm at all the connections. We are told to find the maximum average normal stress in AB and BC. Couple observations can be made here. Notice, first of all, the distance itself is not given in the question. As such, we cannot use moments. Also, AB itself and BC are two force members. Since they are given angles, we should actually use the methods of joints. This is the free body diagram where the reaction at A and the reaction at C is shown here. Because we know that AB and BC are two force members, we will know that the forces runs along the longitudinal direction of the beams. We first need to find the forces in AB and BC before we can compute the normal stresses in them. The forces AB and BC and the external forces 40 kN all meets at the point B. We can thus extract out the forces with the known angles and form a triangle here. This is the force triangle. The 40 kN, which is to the right, AB over here, and BC over here. Remember, the direction of the forces AB and BC must form a closed loop such that it is in equilibrium. Using the sine rule, 40 resolve, which is 40 kilonewtons, divided by sine of 75 degrees will be equals to FAB divided by sine 45, which is equals to FBC divided by sine 60. Upon solving, we get FAB equals to 29.3 kilonewtons, FBC as 35.9 kilonewtons. As you have seen before, the forces in the links are in the opposite direction as computed using the force triangle. As such, FAB itself is in tension and the link BC itself is in compression. As we have seen previously, the link AB is in tension. As such, for AB, the pin itself will touch the outer edge of the hole, and the parts of the link under stress is in red. To compute the maximum normal stress, we will need the smallest cross-sectional area, which is at this region here. For link BC, which is in compression, the pin itself will touch the inner end of the hole, and the parts of the link that's under stress is in red. The cross-section we consider is just that of the red color portion. For maximum normal stress in link AB, we will just need to use FAB divided by the area of the smallest cross-sectional area. We minus itself the diameter of the hole from the width of the link. This is 0.045, which is the width of the link, minus away the diameter of the hole. Then we multiply by the thickness of the link. This will be the cross-sectional area that we consider. For stress, it is just the force AB divided by the cross-sectional area, which is 97.7 megapascal. For the stress in BC itself, the area is just the width of the link times the thickness, and we have this as a cross-sectional area. This normal stress will just be FBC divided by the area, and we have negative 66.5 megapascal, and is in compression. This comes to the end of tutorial 1.